The transistor 1 is of NPN type, and transistor 2, if you observe the difference between these two transistors, okay, see the emitter is outside of this, showing the outside of the transistor, and here the arrow mark entering into the transistor, that is so where we can say that the transistors are of complementary, that is transistor 1 is of NPN, and 2 is of PNP, and 3 is again NPN, so on. Okay, so why it is, let us discuss. Okay, so transistor 1, transistor 2 are both are complementary. Okay, and here the output of the transistor 1 is connected to the base of the transistor 2 here, and the output of transistor 2 is connected to the base of the transistor 3. Okay, and output of the transistor 3 is now as a output, that is the voltage developed across the RC for all the 3 transistors. Okay, so if you apply a signal to the base of the transistor 1, if you apply signal to the base of the transistor 1, then it enters into the transistor, and due to the transistor amplifier action, there is a voltage developed across the RC, and which is now given to the transistor T2. And again, due to the transistor action, as it is in a active region, uh, there is a voltage developed across the collector of this transistor T2, and which is now given to the base of the transistor T3. So again it amplifies further, and which is collected at collector of the transistor T3. This is of about all about direct coupled amplifier. Let us see in detail. Okay, so here is another circuit diagram for a direct coupled amplifier, which is uh, having all the biasing resistors here. Okay, now circuit details of this direct coupled amplifier. The circuit is a three-stage direct coupled amplifier as shown in the figure, which is having three stages, that is three transistors, transistor T1, T2 and T3. And it uses complementary transistors as we discussed just now. Okay, first stage is of NPN and second is of PNP. Okay, the first stage uses NPN transistor, second stage PNP transistor, and so on. And this is because why we are using the complementary transistors. This is because the variation in one transistor tends to cancel the variations in the other transistor. The rise in the collector current and the variations in beta of one transistor gets cancelled by the decrease in the other transistor. Why it should be done? Okay, let us discuss in detail in the next slides. Okay, the output from the collector of the first transistor T1 is fed to the input of the second transistor T2, and the output of the second transistor T2 is connected to the next transistor, that is T3, like that, so on. So operation, how it works. So as the input signal is applied to the base of the transistor 1, that is the first transistor. Okay, it gets amplified due to the transistor action, and the amplified output appears at the collector resistor RC of transistor T1. This voltage drives the base of a second stage transistor, and as it is the output is connected to the second stage transistor 1 base, So it drives the base of the second transistor, and the transistor T2 also amplifies the signal further. The output is obtained across this collector load of the transistor T2. The direct coupled amplifier raises the strength of a weak signal. Of course, the amplifier basic function is raising the weak signal. Okay. The DC voltage at the collector of the first stage reaches the base of the second stage. So, proper designing is needed. Why? Because, so as we discussed in the RC coupled amplifier and transformer coupled amplifier, the coupling elements are used to isolate the DC conditions. Whereas in direct coupled amplifier, there are no such coupling elements to isolate the DC condition. So here, the DC voltage of the first stage reaches the base of the second stage. So we need to take some care while designing the direct coupled amplifier. So what we must do, what we need to do to overcome this problem. Here, there is a drawback of a direct coupled amplifier. Okay, that is a drift problem. What is this drift problem? So the drawback of direct coupled amplifier is the parameters like VBE, that is a base emitter voltage, and beta parameters vary with the temperature. Whereas in RC coupled and transformer coupled amplifiers, by using proper biasing elements and stabilization elements, we are now we can able to stabilize this. But here, direct coupled amplifier, which is directly coupled, and there are no such elements, usually capacitors and inductors. So here the problem arises, and due to the temperature variations, the parameters VB and beta will vary, and this causes the collector current and voltage to change. As the transistor parameters VB and beta varying, so the collector current is also varying, because according to the equation, IC equals to beta times the IB. Uh, Here, this voltage changes. This voltage change appears at a final output, because uh, due to the temperature variations, the voltage, collector voltage and collector currents are changing. And, this change is also appearing at the final output. But actually, we need only the input signal, whatever the input we are applying, that should be amplified, and that we should get at the output. In addition to that, due to the temperature variations also, there is a change in the voltage, and which is appearing at the output. This we doesn't need actually. So this unwanted change in the output voltage, which has no relationship with the input, is called as drift. Because even though there is a irrespective of input changes, the output is changing with the temperature. So this is unwanted change in the output. This unwanted change in the output irrespective of input is called as drift. The drift problem can be overcome by complementary transistors.